Hello everyone. So we are continuing studying 3D graphics and we've got to the chapter 12. So this amount of progress. And chapter 12 is about colors. So I don't know. Shall we read it or not? Because this is just a basic theory. But let's see.
We briefly used and manipulated colors in the previous chapters, but never defined them properly. Here we'll discuss what colors are and start building the scene for the upcoming lighting chapters. In the real world, colors can take any known color value, with each object having its own color S. In the digital world, we need to map the infinite real colors to limited digital values, and therefore not all real-world colors can be represented digitally. Colors are digitally represented using a red, green, and blue component, commonly abbreviated as RGB. Using different combinations of just those three values within a range of 0, 1, we can represent almost any color there is. For example, to get a coral color, we define a color vector as the color of an object we see in real life is not the color it actually has, but is the color reflected from the object. The colors that aren't absorbed rejected by the object is the color we perceive of it. As an example, the light of the sun is perceived as a white light that is the combined sum of many different colors, as you can see in the image. If we would shine this white light on a blue toy, it would absorb all the white color's subcolors, except the blue color. Since the toy does not absorb the blue color heart, it is reflected. This reflected light enters our eye, making it look like the toy has a blue color. The following image shows this for a coral-colored toy, where it reflects several colors with varying intensity. You can see that the white sunlight is a collection of all the visible colors, and the object absorbs a large portion of those colors. It only reflects those colors that represent the object's color, and the combination of those is what we perceive in this case, a coral color. Technically, it's a bit more complicated, but we'll get to that in the PBR chapters. These rules of color reflection apply directly in Graphsland. When we define a light source in OpenGL, we want to give this light source a color. In the previous paragraph, we had a white color, so we'll give the light source a white color as well. If we would then multiply the light source's color with an object's color value, the resulting color would be the reflected color of the object, and thus its perceived color. Let's revisit our toy this time with a coral value and see how we would calculate its perceived color in Graphsland. We get the resulting color vector by doing a component-wise multiplication between the light and object color vectors.
Okay, so we just multiplying source color with the toy color. Interesting.
We can see that the toy's color absorbs a large portion of the white light, but reflects several red, green, and blue values based on its own color value. This is a representation of how colors would work in real life. We can thus define an object's color as the amount of each color component it reflects from a light source. Now, what would happen if we used a green light? As we can see, the toy has no red and blue light to absorb and slash or reflect. The toy also absorbs half of the light's green value, but also reflects half of the light's green value. The toy's color we perceive would then be a dark greenish color. We can see that if we use a green light, only the green color components can be reflected and thus perceived. No red and blue colors are perceived. As a result, the coral object suddenly becomes a dark greenish object. Let's try one more example with a dark olive green light.
Dark olive green.
As you can see, we can get interesting colors from objects using different light colors. It's not hard to get creative with colors. But enough about colors, let's start building a scene where we can experiment in. In the upcoming chapters, we'll be creating interesting visuals by simulating real-world lighting, making extensive use of colors. Since now we'll be using light sources, we want to display them as visual objects in the scene and add at least one object to simulate the lighting from. The first thing we need is an object to cast the light on, and we'll use the infamous container cube from the previous chapters. We'll also be needing a light object to show where the light source is located in the 3D scene. For simplicity's sake, we'll represent the light source with a cube as well. So, filling a vertex buffer object, setting vertex attribute pointers, and all that jazz should be familiar for you by now, so we won't walk you through those steps. If you still have no idea what's going on with those, I suggest you review the previous chapters and work through the exercises if possible before continuing. So, the first thing we'll need is a vertex shader to draw the container. The vertex positions of the container remain the same, although we won't be needing texture coordinates this time, so the code should be nothing new. We'll be using a stripped-down version of the vertex shader from the last chapters.
Okay, so last was camera, so we would need to rename it to color. What the name of the chapter? Colors. 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 Okay. Now we need to rename camera to colors. Okay, now we need to include colors and then update main, include colors. Boom, done. And we have things to work with. So I made Q to exit, and then the real engine Q is go up and E is go down, and I by habit pressing Q and exiting the program, but it's fine. So let's get back to the book.
So the first thing we'll need is a vertex shader to draw the container. The vertex positions of the container remain the same, although we won't be needing texture coordinates this time, so the code should be nothing new. We'll be using a stripped down version of the vertex shader from the last chapters.
Projection view model and vector. Vertex shader. Yeah. And let's get rid of this stuff. So let's see if it's gonna work. Interesting. There is a still texture here. How it is? So huh. So interesting. Colors, fragment shader. So textures, we still getting textures. V text core. So now we need to set the object color and light color, and have this called light color times object color. So we need this uniform vec free so everything should be black now. Yeah, everything is black as expected. So color dot cpp. So we will keep textures, but also we will add bgfx uniform handle object color light color. So I don't think I need to specify its uniform. Object color equals bgfx create uniform object color bgfx uniform type vec free light color light color. It's not vec free, vector free maybe. Should be vec free. So there is no vec free, only vec 4. Interesting. What the heck is going on here? Yeah, there is no vec 3. Interesting, there is only vec 4. Anywho, transform uniform. So we would do set uniform object color where is the book? 105031 1 5 3 1 1 1 1 1 1 1 1. Let's see. Interesting. Colors, fragment shader. Let's try this. Okay.
One thing left to note is that when we start to update these lighting shaders in the next chapters, the light source cube would also be affected, and this is not what we want. We don't want the light source object's color to be affected the lighting calculations, but rather keep the light source isolated from the rest. We want the light source to have a constant bright color, unaffected by other color changes. This makes it look like the light source cube really is the source of the light. To accomplish this, we need to create a second set of shaders that we'll use to draw the light source cube, thus being safe from any changes to the lighting shaders. The vertex shader is the same as the lighting vertex shader, so you can simply copy the source code over. The fragment shader of the light source cube ensures the cube's color remains bright by defining a constant white color on the lamp.
Okay, so we need to create colors, light fs, and it should be vec4 1 1 1 1. All right, and so we have that program, so we need to program light, and it would be light okay.
When we want to render the container object or possibly many other objects using the lighting shader we just defined. And when we want to draw the light source, we use the light source's shaders. During the lighting chapters, we'll gradually be updating the lighting shaders to slowly achieve more realistic results. The main purpose of the light source cube is to show where the light comes from. We usually define a light source's position somewhere in the scene, but this is simply a position that has no visual meaning. To show where the light source actually is, we render a cube at the same location of the light source. We render this cube with the light source cube shader to make sure the cube always stays white, regardless of the light conditions of the scene. So let's declare a global vec3 variable that represents the light source's location in world space coordinates.
Light light position. GLM vec3 light position. GLM vec3 1 2 1 2 1 2 1 2.
We then translate the light source cube to the light source's position and scale it down before rendering it.
Okay. So this is the model, and then so I think everything else I just have to copy and paste. So let's see. So we need to no. Ah. Trans. Trans uniform. And we don't need these, so I think that should do. Oh, light program, right? Program light. Here we go. So we have a light source. Set view transform. Set transform. So I'm wondering if I need to do this. Let's comment this thing out and see. So looks like I can set it up once. Okay. Set view transform. So I can remove this thing. Set view transform. So, and probably I can do it like this. So this is the for loop. So this is the before for loop. This is the after for loop. We need to have I here. We set view transform, and here we updating only model matrix, and here's it, we updating only model matrix. Okay. Okay, so now we are going to chapter 13, basic lighting. Should I remove all these cubes, or should I keep them? I'll keep them. So let's make the commit. Colors. And let's go to basic lighting.
Basic lighting.
Include basic lighting, and colors. Basic lighting, basic lighting, basic lighting. Okay. Main, I forgot to update main. HPP. Basic lighting. Okay.
Lighting in the real world is extremely complicated and depends on way too many factors, something we can't afford to calculate on the limited processing power we have. Lighting in OpenGL is therefore based on approximations of reality using simplified models that are much easier to process and look relatively similar. These lighting models are based on the physics of light as we understand it. One of those models is called the Phong lighting model. The major building blocks of the Phong lighting model consist of three components: ambient, diffuse, and specular lighting. Below you can see what these lighting components look like on their own and combined. Ambient lighting. Even when it is dark, there is usually still some light somewhere in the world, the moon, a distant light, so objects are almost never completely dark. To simulate this, we use an ambient lighting constant that always gives the object some color. Diffuse lighting simulates the directional impact a light object has on an object. This is the most visually significant component of the lighting model. The more a part of an object faces the light source, the brighter it becomes. Specular lighting simulates the bright spot of light that appears on shiny objects. Specular highlights are more inclined to the color of the light than the color of the object. To create visually interesting scenes, we want to at least simulate these three lighting components. We'll start with the simplest one, ambient lighting. Ambient lighting light usually does not come from a single light source, but from many light sources scattered all around us, even when they're not immediately visible. One of the properties of light is that it can scatter and bounce in many directions, reaching spots that aren't directly visible. Light can thus reflect on other surfaces and have an indirect impact on the lighting of an object. Algorithms that take this into consideration are called global illumination algorithms, but these are complicated and expensive to calculate. Since we're not big fans of complicated and expensive algorithms, we'll start by using a very simplistic model of global illumination, namely ambient lighting. As you've seen in the previous section, we use a small constant light color that we add to the final resulting color of the object's fragments, thus making it look like there is always some scattered light even when there's not a direct light source. Adding ambient lighting to the scene is really easy. We take the light's color, multiply it with a small constant ambient factor, multiply this with the object's color, and use that as the fragment's color in the cube object's shader.
Okay, so we just take this thing, copy paste, and it's gonna be good to go. Fragment shade. Right, ambient strength, ambient result for colors will be good to go. Huh? Vec 3, Vec 4. Ah, okay. So we should not do this thing. 4, 4. It's still crashing. Frag color. Ah. GL underscore frag color. Okay. Here we go. Oh, I'm not sure if it's what we want. So let me let me change the background color to completely black. Oh yeah, we do see something. It's very faint. Okay. Okay. Yeah, I think it matches with the screenshot here.
Diffuse lighting, ambient lighting by itself, doesn't produce the most interesting results, but diffuse lighting, however, will start to give a significant visual impact on the object. Diffuse lighting gives the object more brightness the closer its fragments are aligned to the light rays from a light source. To give you a better understanding of diffuse lighting, take a look at the following image. To the left, we find a light source with a light ray targeted at a single fragment of our object. We need to measure at what angle the light ray touches the fragment. If the light ray is perpendicular to the object's surface, the light has the greatest impact. To measure the angle between the light ray and the fragment, we use something called a normal vector. That is a vector perpendicular to the fragment's surface, here depicted as a yellow arrow. We'll get to that later. The angle between the two vectors can then easily be calculated with the dot product. You may remember from the transformation chapter that the lower the angle between two unit vectors, the more the dot product is inclined towards a value of 1. When the angle between both vectors is 90 degrees, the dot product becomes 0. The same applies to theta. The larger theta becomes, the less of an impact the light should have on the fragment's color. Note that to get only the cosine of the angle between both vectors, we will work with unit vectors, vectors of length 1, so we need to make sure all the vectors are normalized. Otherwise, the dot product returns more than just the cosine. See the transformation chapters. The resulting dot product thus returns a scalar that we can use to calculate the light's impact on the fragment's color, resulting in differently lit fragments based on their orientation towards the light. So, what do we need to calculate diffuse lighting? Normal vector, a vector that is perpendicular to the vertex surface. The directed light ray, a direction vector that is the difference vector between the light's position and the fragment's position. To calculate this light ray, we need the light's position vector and the fragment's position vector.
So now we are going to normal vectors.
Normal vectors, a normal vector is a unit vector that is perpendicular to the surface of a vertex. Since a vertex by itself has no surface, it's just a single point in space, we retrieve a normal vector by using its surrounding vertices to figure out the surface of the vertex. We can use a little trick to calculate the normal vectors for all the cube's vertices by using the cross product. But since a 3D cube is not a complicated shape, we can simply manually add them to the vertex data. We'll list the updated vertex data array next. Try to visualize that the normals are indeed vectors perpendicular to each plane's surface. A cube consists of 6 planes.
Okay, so float nx and y and z and y and z. Okay, so this is negative y. This is negative z, so I think I can take this and make it negative. So negative z. Okay, so this one is positive y, so I can take this one. This one is negative x, so it's minus 1, 0, 0. And this one is positive x. Okay. Now we need to update that thing, so it's normal. Oh, it did compile. Normal text coordinates. So let's see, would it explode or not? It's there is a still, yeah, there is a still cubes, so nothing exploded.
Now that we added a normal vector to each of the vertices and updated the vertex shader, we should update the vertex attribute pointers as well. Note that the light sources cube uses the same vertex array for its vertex data, but the lamp shader has no use of the newly added normal vectors. We don't have to update the lamp shaders or attribute configurations, but we have to at least modify the vertex attribute pointers to reflect the new vertex array size. We only want to use the first 3 floats of each vertex and ignore the last 5 floats, so we only need to update the stride parameter to 8 times the size of float and we're done. It may look inefficient using vertex data that is not completely used by the lamp shader, but the vertex data is already stored in the GPU's memory from the container object, so we don't have to store new data into the GPU's memory. This actually makes it more efficient compared to allocating a new VBO specifically for lamp. All the lighting calculations are done in the fragment shader, so we need to forward the normal vectors from the vertex shader to the fragment shader. Let's do that.
Okay, so this is the vertex shader, and we just passing normal. Okay. So we need to update varying vec for a normal. I guess it's like this. Vec for I assume it's like this. So in the vertex shader, position a text coordinate a normal, and output v normal. We just passing it through, right? Normal equals a normal. Yeah. And we need to add uniform light position. Basic lighting, HTTP, BGFX, uniform handle, light pose, uniform. Light pose. And set uniform light pose. Uniform light pose. Okay, let's compile. And in the fragment shader, so this is the fragment shader. Frag position.
Then the last thing we need is the actual fragment's position. We're going to do all the lighting calculations in world space, so we want a vertex position that is in world space first. We can accomplish this by multiplying the vertex position attribute with the model matrix, only not the view and projection matrix, transform it to world space coordinates. This can easily be accomplished in the vertex shader, so let's declare an output variable and calculate its world space coordinates.
Frag position. Vary in def dot. What? Don't do the search. Do the search. No. Search Google. Search. No AI mode. No website. Search. Come on. File must be used to define input-output semantics and type instead of using attribute in and varying in out. This file cannot include comments and typically only one is necessary. This must be used to define input-output semantics and types instead of using attribute. Why? Why it's in French? No, give me English. I want English. Francis. Iglitsk. Give me Russian. No Russian. Украинска. Русский. Русский. Color normal position. Okay, so I can a frag position, and like I say, position 2. It's like a, or I can do 0 1 0 1 like this. A frag position, would it do? So so this is the fragment shader, so we need to go to the vertex shader, and in vertex shader we should specify frag position. V frag position equals why it's vec free? model times model times vec free. So position is vec free. Okay, so we've got frag position, fragment shader. Let me split into basic lightning, fragment shader, input v frag position, output v normal, v frag position. Okay, so normalize normal. Oh wait, this is a wrong place. V normal. Okay. So also v normal. So v normal light position uniform vec 4 light position. So we should do XYZ and v frag position light direction diffuse light color. Diffuse and then vec free result ambient plus diffuse times object color. Ambient plus diffuse, so it should be this. Can I do it like X, like this? I don't know. Nope. V frag position, undefined variable v frag position. Um, oh, assignment of incomplete type. Vec4 diffuse x y z1. Hmm. Diagnostics are pretty good. 28. Not this line. I don't know which line it's complaining. 28. Oh, it's 28 of bean. Okay, bean. Basic lighting. 28. Ambient strength, light color. Uniform 4. Yeah, this line. Maybe it's in the vertex shader. Vfrag position. Oh, it is Vec 4. Interesting. Okay, so we do not need to do where is it? Basic lighting vertex shader. So we do not fragment shader. No, it's a vertex shader. Oh, I'm looking at the bean. Here we go. No. Vfrag position. Yeah, so it should be like this. Unknown preprocessor directive input. Where did I put input? line 17. V-frag position. Where this input came from? Oh my god. Implicit cast from vec 4 to vec 3, line 24. Light deer, V-frag position. Line 24. Line 27. Diffuse light color, diffuse float light color. What the heck? It's still wrong. I do not know. It's still wrong. But they all shaded differently. And this one is... Oh, it's got the texture for some reason. How did you get the texture, my fella? Interesting. Yeah, I don't know. Basic lighting, light FS. How did it get the texture? What the heck? So I don't know. I do not know how to interpret this thing. Also, this one is red, textured, and how this happened, I have no idea. Yeah, this this should. So this is all defined. This is out. How did it get there? Who knows? What's going on here? Oh, my camera again frozen. Oh, how is possible at all? Is it like a cached? So if I comment this thing out, What if I do it like this? Set vertex buffer. Oh, it disappeared. Interesting. Ah. Man. Where did you get this thing? Program light. Load program, load program. What the heck? Sometimes I think I understand stuff and now it just like doesn't make any sense. Set texture 0, set texture 1. Uniform offset. Okay, we are not using offset for a long time, so go away. This is so strange. Basic lighting. So if I do this, would it change anything? It did change. Not sure how, but it did. And it's completely broken. So I think the fragment shade, so like the fragment shader should match with vertex shader. So if there is output, you have to specify input. Otherwise, things would be broken. I'm wondering if I don't think order should matter, but let me see. Should I? If matters or not. So something wrong with the math. Ah, they mentioned this thing, so this is wrong.
In the previous section, we passed the normal vector directly from the vertex shader to the fragment shader. However, the calculations in the fragment shader are all done in world space, so shouldn't we transform the normal vectors to world space coord? In the previous section, we passed the normal vector directly from the vertex shader to the fragment shader. However, the calculations in the fragment shader are all done in world space, so shouldn't we transform the normal vectors to world space coordinates as well? Basically, yes, but it's not as simple as simply multiplying it with a model matrix. First of all, normal vectors are only direction vectors and do not represent a specific position in space. Second, normal vectors do not have a homogeneous coordinate, the W component of a vertex position. This means that translations should not have any effect on the normal vectors. So if we want to multiply the normal vectors with a model matrix, we want to remove the translation part of the matrix by taking the upper left 3x3 matrix of the model matrix. Note that we could also set the W component of a normal vector to 0 and multiply with the 4x4 matrix. Second, if the model matrix would perform a non-uniform scale, the vertices would be changed in such a way that the normal vector is not perpendicular to the surface anymore. The following image shows the effect such a model matrix with non-uniform scaling has on a normal vector. Whenever we apply a non-uniform scale note, a uniform scale only changes the normal's magnitude, not its direction, which is easily fixed by normalizing it. The normal vectors are not perpendicular to the corresponding surface anymore, which distorts the lighting. The trick of fixing this behavior is to use a different model matrix specifically tailored for normal vectors. This matrix is called the normal matrix and uses a few linear algebraic operations to remove the effect of wrongly scaling the normal vectors. If you want to know how this matrix is calculated, I suggest the normal matrix article 1 from Lighthouse 3D. The normal matrix is defined as the transpose of the inverse of the upper left 3x3 part of the model matrix. Phew, that's a mouthful, and if you don't really understand what that means, don't worry. We haven't discussed inverse and transpose matrices yet. Note that most resources define the normal matrix as derived from the model view matrix, but since we're working in world space and not in view space, we will derive it from the model matrix. In the vertex shader, we can generate the normal matrix by using the inverse and transpose functions in the vertex shader that work on any matrix type. Note that we cast the matrix to a 3x3 matrix to ensure it loses its translation properties and that it can multiply with the vec3 normal vector.
Okay, so vertex shader. So here we just did this one, but what we are suggesting, take a normal, U model. So let's see if it's gonna do the magic. It did, it crashed. Ambiguous overload function referencing move. A normal. Like this, maybe. Hmm. 27. I take vertex shader bin. 27. Ah. There is no move. Mat free. A normal vec 4. V normal. We need to put the 0, right? Vec 3 equals temp and vec 4 temp x temp y temp z 0. It is working. It is working. Wow. Do we have easier way to construct a vec 4? What?
Do you have AAA batteries?
AAA battery. How much do we need?
Just 2. Okay.
You're welcome. Okay, so we can do it this way. So let's check it out. So it suggests we can do it this way. Okay. That's so beautiful. That's so beautiful. Shall we make the light to move in the circle? Let me first do some housekeeping. So here, right, we can do diffuse like this. Let's double check if it's gonna work. Yeah, it is still working. So we can do vec 4 here. like this. Okay. Now let's make basic lighting. So light position. Six. It's called 6. I guess we can put it like this. So we would do const auto rot matrix equals that matrix, and we glm rotate, and we would rotate based on seconds around vector 0, 0, 1. And rot mat times. Oh my goodness. Look at this beauty. Okay, so we let's do 4 and maybe -2. Let's see, just tweaking some parameters. 0 maybe, and 8. That's pretty cool. Okay. So let's make the commit. Is it like end of the basic lighting? Specular lighting. We need to do specular lighting. And this is gonna be end of the chapter. Let's do specular lighting.
If you're not exhausted already by all the lighting talk, we can start finishing the Phong lighting model by adding specular highlights. Similar to diffuse lighting, specular lighting is based on the light direction vector and the object's normal vectors, but this time it is also based on the view direction, e.g. from what direction the player is looking at the fragment. Specular lighting is based on the reflective properties of surfaces. If we think of the object's surface as a mirror, the specular lighting is the strongest wherever we would see the light reflected on the surface. You can see this effect in the following image. We calculate a reflection vector by reflecting the light direction around the normal vector. Then, we calculate the angular distance between this reflection vector and the view direction. The closer the angle between them, the greater the impact of the specular light. The resulting effect is that we see a bit of a highlight when we're looking at the light's direction reflected via the surface. The view vector is the one extra variable we need for specular lighting, which we can calculate using the viewer's world space position and the fragment's position. Then we calculate the specular's intensity, multiply this with the light color, and add this to the ambient and diffuse components. We chose to do the lighting calculations in world space, but most people tend to prefer doing lighting in view space. An advantage of view space is that the viewer's position is always at 0, 0, 0, so you already got the position of the viewer for free. However, I find calculating lighting in world space more intuitive for learning purposes. If you still want to calculate lighting in view space, you want to transform all the relevant vectors with the view matrix. As well, don't forget to change the normal matrix too. To get the world space coordinates of the viewer, we simply take the position vector of the camera object, which is the viewer of course. So let's add another uniform to the fragment shader and pass the camera position vector to the shader.
Uniform view position. So we need to pass view position. View position uniform. View position. Compose. Composition. Okay. So now we add this thing. In the fragment shader, I assume. View position. Add this stuff. It's probably should do it this way, right? Specular strength. And we do Control C, Control V, Control C, Control V. Plus specular. View position, frag position, I guess. Our composition is vec free, and light position is also vec free. Oh, interesting. Ah, but I have to do vec 4 here, I see. So it might be reading a little bit outside of memory, right? Anyways, view position, frag position. So view position, frag position, XYZ, light dir, norm, reflect dir, and spec, light color, vec 4, RGB 1. So I think that's it. Hopefully that would do the trick. Of course it did not compile. 35 basic lightning. Lightning fragment shader bin. Oh yeah. 4. I'm not seeing any speculars. Let me comment out diffuse. Oh, there is a specular. Let's make it 2 times stronger. 256. I guess I need to make it closer, right? Basic lighting.cpp. So maybe 4. Let's see. Two minus 4. Okay. And oh, what just happened here? Let's enable diffuse. Cool. So this is the basic lighting.
In the earlier days of lighting shaders, developers used to implement the Phong lighting model in the vertex shader. The advantage of doing lighting in the vertex shader is that it is a lot more efficient since there are generally a lot less vertices compared to fragments, so the expensive lighting calculations are done less frequently. However, the resulting color value in the vertex shader is the resulting lighting color of that vertex only, and the color values of the surrounding fragments are then the result of interpolated lighting colors. The result was that the lighting was not very realistic unless large amounts of vertices were used. When the Phong lighting model is implemented in the vertex shader, it is called garage shading instead of Phong shading. Note that due to the interpolation, the lighting looks somewhat off. The Phong shading gives much smoother lighting results. By now, you should be starting to see just how powerful shaders are. With little information, shaders are able to calculate how lighting affects the fragment's colors for all our objects. In the next chapters, we'll be delving much deeper into what we can do with the lighting model.
Okay. So let's make the commit and call it a day for today. Like optional light position, view position. Basic lighting.
Basic lighting.
Okay. Thank you for watching, and hopefully see you next time. Bye.